Hello, good day. Today is another day. I don't know what day it is because you could be watching this on any day, in any month, and any year. So, whatever it is, good day. Today's topic is 1.08 graphing. Oh, you were hoping I'd use that voice for the whole video, did you? I don't think I could keep it up that long. But anyway, 1.08 graphing. This is the final topic for Unit 1, Science is a Verb. So if you ever wanted to get a good laugh and learn how to graph, well, then just follow along so you don't get it wrong. Here we go. The entire purpose of graphing is to allow you to make predictions. See, when you have your data, if you graph it, then you can make predictions about information that you didn't get data for. What exactly does that mean? Keep watching. So, the scientific method is used to solve problems. It can explain observed phenomena like the universe, where did it come from? And it can be used to predict outcomes. For example, on a weather map, you can use a weather map and data to figure out, well, exactly where is this rainy low pressure system going to end up tomorrow. Graphing does the following. First, it illustrates the relationships between the tested variables. Is it linear? Is it a different function? Is it direct? Is it inverse? Is there no discernible relationship? And so there's many different kinds of graphs you can do as well. We're going to be dealing here with graphs that involve data points that, well, you'll see. I don't want to spoil anything. It provides a basis for determining mathematical relationships between variables. So, for example, if it's a linear relationship, you know that as one thing goes up, and the other thing goes up. And then the slope determines how much it goes up by. So in this particular example, this graph tells us that as we increase the pressure, the volume decreases. And so we can make predictions about gas behavior based on this. It allows a researcher to make testable predictions. So when you do a graph, you can actually compare your results to your predictions to see how well your model held up to actual data. So how do we build a graph? Well, you do not need hammers, but you do need axes. Well, axes, I guess would be the plural, labeled as following. You have your dependent variable with the unit on the y-axis and the independent variable with its unit on the x-axis. The most common mistake I see people make is either switching them or leaving out the unit. Okay, so make sure you've got that. A number range. Now, you're going to have a data table, and so you're going to know what your lowest value is and what your highest value is. So just figure out how many divisions between each hash mark. So like that. Let's say you go from 0 to 60, and then you just want to put in intervals in between, regularly spaced intervals. You don't want to actually put your data numbers down here. You're going to be interpolating to put those in. I'll show you what I mean in a moment. The scales do not have to be the same on the X and Y axis. They just don't. They can be. There's no rule against it. But they don't have to be the same size interval. Let's continue. You want a title, and the title will be whatever is on the y-axis versus whatever is on the x-axis. So if this is temperature and this is time, our variable would be temperature versus time. You don't have to come up with a snazzy title for it. You're basically just saying, we're changing this, and this is going to change as a result. Data points based on a data table. So let's say that our independent variable is 0, right here, and the dependent variable is 2. Well, if this is 0 and this is 5, this would be like 2.5, so 2 would be a little less than that, so we just estimate, and then we put a decimal point. Okay, next up, 10. Well, let's see. 10 on the x-axis. We have to go to 4, which is a little less than 5, would put us probably around there. See? Yep. And then you pop your data point. Okay, 20. would be 7. Okay, so here's 20. Here's 5 and 10. So 7 would probably be somewhere around like there. Zoop, zoop. Hey, look at that, right on the dot. And then 30 would be 9. So 30 would be just below 10. So let's see, that's 30 and 10 is there. So 9 would be about there. Zoom, zoom. A little bit off. Okay. And then 40 is 12. And so here's 40, and 12 would be above 10, but below 15, closer to 10 than 15. So let's say right around there. And okay, close enough. Notice I leave myself room to extrapolate. So, for example, I know information about 0 to 40. What if after I do the graph, I want to find out information about 57? Then all I have to do is extend the graph, and then I can actually make a prediction. More about that in a little bit. So, those are your data points. Next up, draw point protectors. These can be shapes, usually circles, around the data points. You can use triangles or squares or hearts, moons, clovers. The idea being that you want to make sure that the data point stands out so that when you put the line over it, the line isn't hiding the data point. Also, sometimes you may graph more than one thing on the same graph. You can use circle point protectors for one of your lines, or triangle point protectors for a second line, or square point protectors for a third line. Of course, if you were graphing in color, you could just use different colors, but you would still want point protectors so that the line doesn't accidentally obscure your data point. And a line of best fit. Now, how we achieve this line of best fit is going to be the subject of our next topic of discussion. And my cat has just sat down between me and my microphone, and she is sniffing the microphone. Hello, Priya. Okay. Let's say your data fits a roughly linear progression, and it's not a straight line. Should you connect the dots? No. What you could do is take multiple readings and average them and use those averages to plot it. That's going to give you a much better linear relationship. But what you do is you just simply represent the slope of those data points the best you can so that the number of the total distance between of the points above your line of best fit is about the same as the total distance of the points below the line. So, for example, this line right here, it doesn't really represent the slope of those points. So it's too steep. So that wouldn't be a good line of best fit. What about that? Well, you'll notice that you have 3 data points that are under the line and 1 data point above. So if we add up the distances of the 3 data points below and the 1 data point above, it's really too high. If we lowered this a little, that could be a good line of best fit. What about that? Well, here we have 3 points above and nothing below, so this is just too shallow a slope. It doesn't well represent the slope of the curve. About that? Well, it's not perfect, but we have 1 above and 1 below, and their distances to the line are similar. You could draw this slope just a hair more slopey if you wanted to make it perfect. If you're working on a computer, all you have to do is use something called linear regression, and it will draw the line of best fit for you. But if you're just eyeballing it on a graph, just do the best you can, right? Nobody's going to go crazy if you don't get it perfect. If somebody does go crazy, then don't sue me. Okay, so that is just right. Now, respect the y-intercept. When you do your line of best fit, y equals mx plus b, right? M is the slope. B is where the line crosses the y-axis, all right? The y-intercept doesn't have to be 0, right? If it was y equals mx plus b and b was always 0, we'd forget about this part and we'd just say y equals mx and let it be like that. Now, if the line does start at 0, great. But if by extending your line you go to 0, well, you've just changed your slope. That's not justified. So if you're going to extend, nope. If you're going to extend your line to the y-axis, make sure you maintain the same slope the whole way. Okay, how big should your graph be? at least half of the page that it's drawn on. The smaller it is, the harder it is to read. So too small, too small, too small, too small, too small, getting better, getting better, getting better, acceptable, more acceptable, and OMG, this is awesome because now we can really read it. The bigger the graph, the more easy it is to read. So make it easy, especially on us old people who have difficulty reading and stuff because, we need glasses. Okay, direct relationship. Here's the different kinds of relationships you can have between your variables. So if one variable increases and the other variable does also, well, that would be a direct relationship. So just like the ones we've been graphing. That's a nice direct relationship. As time increases, the distance increases as well. Right? Let's say you're driving a car. Well, the longer you drive it, the further you're going to drive. Okay, that's great. All right. Although if it takes you 40 seconds for your car to drive 12 centimeters, yeah. Okay. It does not have to be at the same rate. Remember, m, the slope, will be dependent. And of course, your axes are not the same scale. So don't even worry about it. Inverse relationships. As one variable increases, the other decreases. So you can see here, as pressure increases, the volume decreases. This would be an inverse relationship. Now, you can also use your graph to make predictions. If you're making predictions within your data set, we call that interpolation. So we know information about 0, 10, 20, 30, 40, but what if we wanted to know about, let's say, 22? Or what about 37? Well, what we can do is just go to the axis you know the information for, go up to the line, and then shoot across to the other axis and estimate the value from the other axis. And in so doing, you can make a prediction. That's called interpolation. So how many centimeters will be traveled in 26 seconds? So we go to roughly 26 seconds. Put a little X there, not a circle with a data point because it's not data, it's just a prediction. I'm putting an X there. And then I'm going to shoot over to the other axis. And that looks like it's a little more than halfway between 5 and 10. So let's call that 8 centimeters. All right. You can't do any more than you can't call it like 8.2 or something because since like these are the ones. All right, if this is like 1, 2, 3, 4, 5, then you'd have extra information to go by. But this 5 doesn't really help you all that much. In fact, if that 5 wasn't there, you'd still estimate that it was around 8. So you can't go any further. It's just like when you read from a ruler, right? You can only go one place smaller than where it's marked. And this is only really marked to every 10. Usefully to every 10. Extrapolation means you got to put a little extra on your graph. So always leave yourself room to extrapolate. This helps you make predictions beyond your data set. So we know information about 10, 20, 30, and 40, but what if we wanted to get information about 54? Well, then we'd have to extend our slope and then make our prediction. So in 53 seconds, what we do is we extend our graph, we continue the slope, we go to 53 seconds on the axis we know, put a little X on the line, and then shoot over to your other axis, and well, that looks like pretty much 15. So you read it just like measuring devices, only one place smaller to where they're usefully marked, and this 5 doesn't really help you. So really to every 10 is where it's marked, which means you can estimate only to the nearest 1. And that's how to read a graph and the different relationships and how to make a graph. Rather a lot, but it's very useful, and you will be making use of this once again all year. And with this, we end Unit 1, Science is a Verb. Please take the time to go back and rewatch anything you may need additional help with. Thank you very much, and I hope you're having an absolutely wonderful day. I know I am. It's actually Monday, May 4th, 2020. 2020. Yeah, and right now we're in the middle of being locked down because of this nasty virus. So if we're still dealing with this nasty virus, please stay safe and healthy. Bye.